Hello, my name is Jack Dangarra. I'm a professor at the University of Tennessee and the Turing Award winner for 2021. It's an honor to be invited to the 2022 China International Digital Economic Expo. Today I'm going to give a talk about an overview of high-performance computing and the importance of AI and machine learning. When we think about science and how science is carried out, it's usually done by theory and experimentation. Theory is a paper and pencil calculation. Experimentation is where we actually build a system and use that system to understand the theory and to verify that theory. There's interplay between those two. Because of the experiments, we may change the theory, and then because of the theory, we may be able in a better position to construct experiments. Sometimes it's too difficult to build an experimental facility. It's too expensive, perhaps, or it's too slow to carry out the kind of thing we would like to do in experimentation. Think of climate modeling. Think of colliding two galaxies. That's an experiment that we can't actually carry out unless we do a simulation of that. So high-performance computers are used to help understand and drive forward scientific discovery. It's sort of the third pillar. It augments theory and experimentation with simulation. And that simulation is carried out on computers, and the more advanced computers are supercomputers, which are used, and those supercomputers really drive scientific discovery today. So a typical supercomputer is composed of a commodity processor. Think of a processor. On that processor are many, many cores. It's called a many-core chip. Each of those cores represent a processor which can carry out independent operations. And we're going to be using that collection of processors to help do a computation. So we think about taking that chip. We're not going to be satisfied with one chip. We think about putting multiple chips on a board, and that being the basis for our computational device. But we really want to boost the performance. So we think about adding to that collection something called a GPU, a graphical processing unit. And that graphical processing unit is capable of giving us many more floating point operations, the basis for doing our scientific computation. So the commodity chip plus the GPU form the basis of doing our computation. We offload things to the GPU, and it helps to accelerate that part of the computation. We're not going to be satisfied with just having one of those boards. We think about populating a cabinet with multiple boards, each of those boards having multiple chips and multiple GPUs on it. And of course, we're not going to be satisfied with just one cabinet. We think about composing a supercomputer based on multiple cabinets, connecting them together with a high-performance switch, and putting them in a room. And that room has a footprint, an area roughly the size of 2 tennis courts, full of racks of these high-performance computing parts connected together, allowing us to carry out a single computation across that ensemble. This graph represents what's happened to high-performance computing over the last 29 years. It comes through from something we have called the Top 500 list. We have a ranking of the 500 fastest computers. And on this graph, the red dot represents the fastest computer at any point in time. The fastest computer today is at 1.1 exaflops, or 1.1 times 10 to the 18 floating point operations. And the computer that just made it on the list is there at 165 petaflops. So that gives you the bracketing, if you will, for high performance computing. The blue dot is the sum of the 500 machines, so we could track the progress that we've made over time. So you can see where we've been. Back in 1993, the fastest computer was at 60 gigaflops, and the lowest computer was at 422 megaflops. The fastest computer back in 1993 was something called a thinking machine CM5. It had 1,000 processors in it. It was at Los Alamos National Laboratory, used to carry out nuclear weapons simulation. My laptop, the thing I'm using to give this presentation, I can run the benchmark, and when I run the benchmark, I get 426 gigaflops of performance out of it. So that's faster than the fastest computer that we had back in 1993. So stunning changes have taken place in the technology that drives high-performance computing, and we see that taking place today. In fact, my laptop is the equivalent of the fastest machine in 1997. That was a machine made by Hitachi. It had 2,000 processors, and it was at the University of Tsukuba. So we're talking about exaflops. So what is an exaflop? But first, let's talk about one flop. One floating point operation is an add or a multiply of a 64-bit set of numbers. So one add or one multiply, that makes up one flop. And an exaflop is a billion floating point operations per second. 10 to the 18 floating point operations per second. So if we, just to get a handle on that, if we think about all the people on the planet, and we ask all the people on the planet to do one operation per second, it would take 4 years for everybody on the planet doing one operation per second to equal what the supercomputer can do in 1 second. So that's what exascale brings to us, that amount of computing power. This is a list of the top 10 computers. Just how to read this is the machine at #1 position is a Department of Energy machine. It's at Oak Ridge National Laboratory. It's called Frontier. It's integrated by a company called HPE. It has AMD parts in it, AMD processors and AMD GPUs. It has 7.7 million cores. It ran the benchmark at 1.1 exaflops. It reached 55% of the theoretical peak performance, and it used 21 megawatts of power in order to drive this machine. So a lot of power consumption for these machines, and that's going to become an issue as we go forward. Just looking down the list, there are 5 machines of the top 10 in the U.S. 2 of them are in China. The Sunway Tahu Lite is there, as well as the Tianhe 2A. The Sunway machine is interesting in that it does not use commodity processors. It's a special processor that was designed in China that's being used to drive that computer. The Tianhe 2A uses Intel chips for the commodity processor, and then they designed a specialized accelerator at NUDT to help boost the performance. France has a machine, Finland and Japan round out the top 10 list. If we take a look at where those 500 machines are located, what we see is that China has 173 of the 500 machines. So they have the most supercomputers. US has 128, and you can see where the other ones are located. If we look at the producers of supercomputers, who makes the supercomputers, China makes the most supercomputers. And the 5 companies that are involved in China making the most supercomputers are companies like Lenovo, Sugan, Inspur, Huawei, and NUDT. So those are the manufacturers of those supercomputers, the integrators, if you will, of those supercomputers. It's rumored that China has 2 exascale computers, but they haven't run the benchmark, and it hasn't been submitted to us so that we can enter them on the list. The Ocean Light is the machine that's in Shandong province. It's a machine that's based on the Sunway processor, the earlier one that's on the list today. And the other machine is the Tianhe 3. It's a follow-on to the Tianhe 2A. This machine uses an ARM processor together with that matrix accelerator to help boost the performance. When we think about high-performance computing, we think about a small amount of data coming in, a lot of computations going on, and then a lot of data being produced. And an example of that is when we look at climate modeling. We have a small amount of data going into the model, and it generates this enormous amount of information which shows what's going to happen to the climate over a long period of time, and then we visualize that in a movie. That's different on the data-intensive side. Data-intensive side has a tremendous amount of data going in to do the building of the machine learning apparatus, and then a small amount of data that we need to come out when we actually use that machine learning device. So typically we see scientific computing with a small amount of data, that data being represented as 64-bit operands that are going to be operated on. We get 64-bit results out, and we need that for the fidelity of our solutions. With machine learning, we don't need that much accuracy. We can get by with 16 bits going into the machine learning and then coming out with a 16-bit solution. So today we've seen machine learning and artificial intelligence. They've been around for a long time. So why now is it so important? Today we have this flood of data that we have. So we're able to construct our models for machine learning We have this increased computational power in the form of accelerators that can be used to help with it. We have this growing progress that's been made in algorithms that help researchers do things better. And we have this increasing support from industry. So all of those things lead to machine learning and artificial intelligence being very important today. Artificial intelligence is a broad area. It covers machine learning, natural language processing, expert systems, vision, speech, and robotics. We see machine learning being used in many areas of scientific computing, from climate to drug to materials design and high energy physics. In the future, our high performance computers will probably keep this CPU and GPU for the accelerators, but we'll add other accelerators onto the list. Maybe those accelerators would be for machine learning, neuromorphic computing, maybe quantum computing, and maybe even optical computing that we could use on our supercomputers. I want to thank you again for the invitation to be with you today. I wish you great success in your conference. Bye for now.